Good morning, everyone. We will have on frequent topics.
Harsha, your voice is very feeble for me. I can't even able to make out what you are trying to say.
Yeah. I have come closer to the laptop. Now, is it clear? Is it audible now?
Not it.
Now.
Yeah, can you speak something because I couldn't able to make out.
Yeah, I have come to the. I have come very closer to the laptop microphone, and I am talking to you now.
Yeah, now it is better.
Is it clear now?
Yes, better.
I will go like this, right? Yeah. Today, as per the discussion, we will go through the concepts of the spatial configurations, kinematics, mobility, and perception. After that, we will get into the concepts of path planning, collision detection, obstacle detection and identification. Then we will discuss a bit about what is the A star algorithm and A algorithm. I hope already you have some knowledge about the best first search algorithm in AI, if I'm not wrong, right? So these are the contents that we are going to deliver today. As opined in the earlier section, I will reduce the maximum of theory and we will go into the simulation of robotics. But anyway, we
Sorry,
require.
Harsha. I cannot able to make out what you are trying to say today. Because last class has completely gone for the task, to be precise.
Okay. So tell me what you want, what we will do today.
No, basically your voice is getting slowly reduced, the pitch or the frequency.
Yeah, it
Okay.
was now it is clear, right?
Yeah, all of a sudden it is going down.
Dr. Harsha, if you can come closer to the mic and speak
Loudly.
loudly, I think that would help. So Gopi, today's, if you see, earlier it was only pie game, right?
Yes,
The kind of use cases that Dr. Harsha is trying to build as part of the lesson plan, today would be a slightly different one compared to what we started last week, right? That's what
yes.
it has been
We
written
will be
on
simulating some
obstacle detection and identification and path planning. Sri Harsha, are you speaking loud, please? We are not able to hear. Right?
Yes, ma'am. It is very feeble. I'm sorry because probably the systems, laptops, speakerphone or something could have some issues, but it's really feeble and all of a sudden the voice goes to zero.
Actually,
Can you hear?
yeah, I'm able to listen here to your voices very clearly.
We are able to hear each other. Your voice is quite okay now, but please keep up the same distance and
Is this okay?
and the
Is this okay,
pitch.
ma'am?
Yes, yes, this is better.
Everybody,
Yes,
is this okay right
okay.
now? If this is
Yes, it
okay,
is
please
better.
tell me that we will continue like this.
Yeah. Yes, it is better. See, Gopi, this module and all that is planned ideally in a class setup. But you know that because it's the last module and we are also not able to bring all of you here for a real demonstration sessions. Our plan was to bring in the robotic.
We will do simulation of all the aspects, whatever we have discussed.
Yes. Yeah. So let the module go on as per the lesson plan, Gopi, and let
Sure,
us
ma'am.
look at next week towards the end, Dr. Simha also would be joining so that you all get a complete picture on what is that we want to convey through this module. Okay.
Sure,
And
ma'am.
you are welcome to come to the campus. We have actually lined up with the EEC department, which has a robotic lab, right? They have
Okay.
multiple components and a very dedicated lab on this. We have a robo humanoid where some of our modules are also running. You can come always and fiddle with if you want a demonstrable piece of all these things. But right now, on an online mode, this is the best that you would have to. But doesn't mean that you have to compromise. Let's listen to no to the these modules which are on a simulated platform. Okay.
Sure, ma'am. Thank you.
Yeah. Yeah. This session we
Yeah.
will discuss
Please,
about.
please go ahead, Dr. Sri Harsha. Please go ahead and little loudly, please. I
Yes.
mean, we cannot keep telling this because it is going very, very slow. Please.
Is it now right now audible, ma'am?
Yes, yes,
Is this
audible, but
okay?
keep up the same pitch,
This
please.
only I will
Thank
keep.
you.
This page I'll
Yes,
keep. Okay. Right.
yes, thanks.
Fine. Okay. And this session we will discuss about the concepts of spatial configurations, kinematics, mobility, perception, obstacle detection, object detection and identification, and some practical things about the obstacle detection, object identification, path planning, and finally we'll talk about the A-star algorithm. Okay, and almost all as a student of AI, you must be knowing about that BFS, best first search algorithms and everything. So it will be very easy for us to uh, understand about A-star algorithm. Okay, as a first thing, we will discuss about what is called the spatial configurations of, or what we call as a configuration space. Right. A configuration space is a space where it is the entire. It is called as a entire world, and this in this world the robo and as well as the objects which are interacting with the robo will be represented. Okay, and this space is also called as C space technically here. Okay, the configuration space is consisting of all the components like robo, other parts or other objects, and where all these are lying in the configuration space and they form or they comply to some kind of topology, right? And there are several kinds of topologies that we can understand and in this concept of spatial configurations. Yeah, topology is a very challenging area where we have to understand the depth of the space where we are working on the where we are working with robots, and particularly when it is about that what is called the motion planning. In motion planning, we have to understand about the various connectivities and possibilities of reachabilities of the objects when assigned to the robots, and the robots move through or do some kind of locomotion activity through some path and they reach the destination and do the tasks. A topological space is a concept here which is in the configuration space, which means that it is the basic uh, heart of the topology, and where a set of elements, a set of points which are available, a set of locations on the configuration space, a specific set of points on the configuration space, they form into some kind of a shape or connectivity, and these are called as the topological space. A topological space is a superimposed layer on what is called the configuration space, what we can observe. Okay, and this particular topological space, which is particularly used for a task when a particular robot moves for a particular task, and this will connect certain points, and this particular points and the actions of the robot is considered to be as what is called as a motion planning of the robot, and it is called as a manifold. And manifolds are used in motion planning and confinement of true structure of the space of the transformations to resulting configuration space and so on. Okay, so basically what we say here is there is a configuration space, and this configuration space has a number of points, and on these points and number of locations, right? And these particular points, all these points are not touched by the robot for each and every task. Okay, certain points only are touched for a particular task, and all the possible points which are all the possible points are what you say, the set of points which are related to the particular task are considered to be as what is called a topological space. And this particular topological space containing number of points and number of actions to be done by the robo in each and every point, a specific series of actions and the number of points totally is called as a manifold. Okay, and here this manifold contains what is called the robo activities and as well as the specific set of locations which can make the robo achieve the task accomplished successfully. Okay, and these things are again having what is called the number of points, and how actually at the core level the robo moves from one location to other location and accomplishes the task is based upon the connectivity of these points within the manifold, within the topological space, and the path described by these particular points. Okay. That's actually here what we have the very essential things to understand the spatial configuration is the configuration space is a C space. Configuration space is nothing but a domain, and it is a world which contains what is called all the uh, movement zones where this robot can move. Okay, all the movement zones of the robot are called as the configuration space. Okay, within this configuration space, the robot is given a task, and the robot moves from one location to other location and accomplishing a task. Okay, and this particular configuration space contains number of points, number of locations. Okay, let us say if the robot is moving in some straight line, there is a starting location and ending location. Okay, starting point and ending point. Okay, and otherwise if that is moving, if it's not a straight line, if it's not a straight line, if it is like an L-shaped line, if it's an L-shaped line, there will be a start location, an intermediate location, and an end location wherever the angle, right, where here we will get
Harsha,
have
we
various
lost you
number of
sometime.
points. Yeah, yeah.
So when you say that the robo is planning to move in a straight line, which is a pre-feeded data, or it is being captured based on the.
Yeah, whatever it is, it can be, it is based upon the training of the robo, whether it is an autonomous or non-autonomous. Okay, if it is an
Okay.
autonomous robo, then it will be given the path beforehand. It will be given the path beforehand, and it will move accordingly to the given feed of path. Okay, if it is a non-autonomous robo, then we have to give at every instant some instructions and ask the robo to follow the action.
So if we have to give means, for example, if the topography that which is being used by the robo was not plain or undated topography. So
Okay.
let us assume that case, okay, or an object finding in between the topography, unexpected object finding in the topography. So if it becomes an autonomous body, how it is going to take the decision on what kind of
And non-autonomous robo, and if it is not having its own topology, then it cannot start its task. It cannot start its task on its own if there is no defined topology for the robo. If it is a non-autonomous, if it is an autonomous, and if the topology is known, then only the robo can start its task.
Okay, so that is the predefined condition.
Yes, 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 yes. See, unless we give the input to the robo, it cannot process, it cannot move forward. We have to give the input path to the robo. If the input path is not given, then robo cannot move, even though it is in autonomous. See, in autonomous robo case, it is a different case where the set of all the points are given to the set of points in the configuration space are all given to the robo. Means the robo very well knows about the configuration space, the what's called what you say the whereabouts of all the objects available in the space. Okay, once if it is known, all the entire dictionary of the space is known. That is what the type of objects, where they are laying, and what is the distance, and what is the coordinates, and what is the entire area. If everything information is known, then it may do any autonomous task. Okay, and if it is not an autonomous task, if it is not an autonomous robo, if you do not give path, it cannot go on forward. Okay,
Okay.
right.
So how are we feeding the latitudes, longitudes, and the topology into the configuration file? It is basically from an ad hoc movements, or it is basically because we are making sure that there is nothing object, all these conditions being transferred in the configuration file. You mean to say, which is not
This is not a
the
configuration field. I am talking about configuration space. I am
configuration space.
Yeah,
Okay.
I'm talking about configuration space. A configuration space is something like the space where the robo can move around. Okay, and robo can interact with the objects. The objects which that robo interacts and the robo itself, and this is in a zone, and this is basically defined here in a mathematical way called as the configuration space.
Okay.
Right? Okay.
Got it.
This is also called as a C space, right? Okay, and here in the configuration space, it is observed that there are so many points that where the robo can move along and can do some tasks. Okay, and these points, there are so many points available in the configuration space, but all these points are not suitable or not necessarily touched by the robo for or while doing a task, right? So some points are only used for, some points are not used. Okay, and where in this case certain points which are connected, which are available and which are connected, and that is available called as topological space. And the robo action, the motion planning with respect to the topological space is entirely called as manifold. Okay, and which defines a path and a connectivity for accomplishing the entire task. Okay, so just here I want to give you that information about what is the configuration space in the system. Yeah, you have given some message in the chat box. I'll just get into the chat box. Yeah, I have given you that answer right now. We have discussed about that. What is given in the chat box, right? Well, so that is that. Just I want to give you that information about the configuration space. Now let us get into the concepts of what is called the kinematics of the robot. See, robots can be a humanoid structure, or robots can be a manipulator also, right? And these movements of the robots are based upon what is called the joints and arms. The joints and arms do the activity of the robo, and the robo moves. Okay, the kinematics in robo consistently applies to the geometry, and the geometry is represented in multi-degree geometry, and this multi-degree is a multi-degree freedom kinematic chains that forms the structure of the robo, and the links provide rigid components and joints provide free rotation or translation, and a unit of rotation or a translation influences the subsequent action of rotation or translation, which is a kinematic chain, right? Where there are what is called internal internal kinematic chains and external kinematic chains or reverse kinematic chains, there are so many categories of kinematic chains which you can understand. So here is this a forward kinematic and a inverse kinematic. Forward kinematic is that it is it describes about the joint parameters and computes the configuration of the chain where to reach the task, where to reach the task. That means a robo manipulator or a robo contains number of links and joints, and here the geometry of the geometrical angle of the links at every joint describes right from the robo direction to the end effector. That is called as a forward kinematics. This is called as a forward kinematics. Inverse kinematics or reverse kinematics is the concept that where the last link or last arm will move to the end effector, and accordingly it will adjust the location of the robo by computing the angles and strengths or moments reverse in the reverse direction towards the robo from the end effector. That is end effector is that the end of the limb or the end of the what is called any arm, or we can say, right? And this again is related to some kind of time derivative, and if it is related to time derivative, then it is called as a robo Jacobian. Jacobian has introduced the concept of this time for making these movements of arms and links according to the time it moves to the location, and the end effector reaches the task area, right? And these arms have both angular velocity and linear velocity. The vector is defined here as a matrix which contains the angles and distances of both angular and linear velocity of the end vector. And this vector, what is described, is called as a twist. Okay, and that's about what we have. Some information about what is called kinematics of the robo. And the mobility of the robo comes from the different methods how the robo moves. If it is not a manipulator, then it has so many kinds of locomotion operations or locomotion activities. And basically, if it is a legged robo or a wheeled robo. If it is a wheeled robo, then the wheels of the robo are typically quite energy efficient, and the servo motors will move the robo exactly without having to go into any other external momentum or kinetic forces, which are which will influence the operations to go beyond the borders of the expected configuration space. Okay, so the other one is the legged robots. The legged robots, there are three-legged robots and multi-legged imitate alternate motion of each and leg, animate a walk kind of action. A walk kind of action is animated by each and every leg, and this will be a alternate motion, and this causes what is called a leg moving with looking like a kind of an animal or an insect or so on. Like these various types of mobilities are there: walking, rolling, hopping, metaclonal motion, slithering, swimming, and brachiating. Walking is something like a pod which moves from which holds the weight of the robo on one leg and other alternatively on other legs, and moving all the legs synchronously is what is called walking. And rolling is that where the robo moves and then rolls for turns, for left turn or right turn it rolls, and then again stands on the legs and moving. And hopping is that it jumps into all the four legs, or see all the pods are just like that, what is called they are compressed and they are enhanced, and so that a hop kind of activity with a flexible arms and rubber pads are done. And metachronal motion is something the all the wheels, all the legs of the robo will move in same direction at a time. See, the robo contains legs at both left side and right side. All the legs of left and all the legs of right will not move at once. So all the legs of right will move once, and all the left will move next time, and so on. It moves like a what is called a very gigantic mechanical machine, and that is called as a metachronal motion. Slithering is how the scales of a snake, how the scales help a snake to move forward. Similarly, here also instead of legs, there will be some kind of leg joints which are holding the ground, and the leg joints will slide up and slide down, and a movement is caused, and it moves like what is called a snake. And swimming is that uh, moving off the limbs forward. First front limbs will be moved forward, and then the back limbs will be moved forward once again. And this what is called is something like what you say, a kind of hydra movement is seen, that is called here swimming. And brachiating is a concept of what is called uh, rotation and again standing on legs. Rotation and again standing on legs is a type of mobility. Like this, various kinds of mobilities are there, which it's just only for our information, just what we understand. There are mobilities of robo. And the other important thing in the robo characteristics is the perception. Perception is basically done by sensors. Various kinds of sensors will be added up to the various kinds of sensors will be added up to the robos, and where the robos will act as if they are AI driven. Okay. Perception is understood as what is called as an uh, internal part of inherent part of a robo, and that is what is makes robo. So when we come to the picture, what is called robo, and a robo is said to be always an intelligent. Okay, always an intelligent with respect to a particular domain of task or a generalized one. So more generalized robo is not possible right now. Okay, a specific robo for a specific task is possible. Here, a combination of various kinds of sensors will make a robo as a AI01. The sensors basically are of three types, which we can say sensor. Uh, the perceptions are of three types. We have sensory perceptions, visual perceptions, and some hybrid perceptions. And lidar is one of the thing. Light detection and ranging is one of the thing where by means of the laser lights are illuminated, and the concepts of what is called the reflections are taken back, and the reflection is traced based upon the reflection and based upon the shadow, or based upon the illumination of the reflection, the object is identified. And when you come to the point of sensors, there are so many kinds of sensors. Position sensors, pressure sensors, temperature sensors, force sensors, vibration sensors, piezo sensors, fluid property sensors, humidity sensors, strain gauges, photo optic sensors, flow level switches, and there are so many kinds of sensors available, where these sensors will generate data and send analog data to the GPIO kind of boards in the robo setup, and where the GPIO boards will translate the data and will give the data to the programs, or programs which are written in the Python or whatever the programming language, which rely on operating system, will read these sensor data using some port information, and will convert the data into data sets. Okay, and where these data sets are used for analysis and other kind of things. Okay. A very important thing in this session is about the obstacle detection. When a robo is moving in a configuration space, the robo is not always expected while doing a task to move freely in the configuration space. Where in the configuration space we observe that there are so many other objects available, and when the robo moves, say autonomously or non-autonomously, if the robo moves, there is a chance, or there is an opportunity that this robo will meet an object en route, right? When the robo moves, and if it cannot further move after some distance, which means that there is a kind of an obstacle for the robo. The robo is identified as it has faced an obstacle, and this obstacle can be in different forms. It is to stop the robo for an action, or it is also that, yeah, it is to stop the robot for a particular action, or something like, say, giving a warning to the robot that it can stop here and do the task or whatever, or it cannot go further, like that, or it may be an interruption of the task also finally. So this is basically based upon what is called the the perception how the robot receives that it is an obstacle, right? Well, in the configuration space, obstacles are always random objects or random points in the configuration space where they are employed to stop the robot. And this obstacle detection complies with what is called the path when the robot moves in the path. And this is actually the thing again in well, when the robot moves on a planned path or a non-planned path. Okay. For this, actually, what we have is a motion planning is there. Robot motion planning. We define the path before the robo moves, and we give it to the robo, and robo exactly moves according to the defined path and achieves the task, accomplishes the task. Okay. And in this, when we consider the robo motion planning with regard to the obstacle detection, we have to define a path that it cannot contain, it does not contain any kind of obstacles. And how do we know that there are obstacles in the path? So for this, we have to analyze the configuration space and the objects of the configuration space. Okay. And in this example, what we can see that A, if you consider as a robo that is set up in the configuration space, and if that O be the obstacle in the configuration space C, there is a quaternion Q, a 4, a quadruplet. Okay, quaternion is a quadruplet, and where you can find the properties of the robo configuration. The basic properties of the robo configuration is nothing but the location of the robo configuration, that is the coordinates of the robo and the space occupied by the robo. The coordinates of the robo are the left top corners or bottom right corners or whatever, or bottom left corner or a top right corner. These are the coordinates. Okay, assuming to be that this robo occupies almost all a rectangular space in the Cartesian plane. Okay, a configuration space you may also observe it as a kind of a Cartesian plane, and where you will find the entire Cartesian plane is filled with a number of blocks. Okay, number of blocks, and the robo moves on the path, and the robo path is defined with number of blocks also. And the presentation of robo in the configuration space will be on number of blocks. If it is a very tiny robo, it may be a single block. If it is more than that, maybe more than one block. And this location where this robo is placed in the configuration space is defined by a quaternion. That is what the basically observed as what is called the characteristics of the robo. And this quaternion of the robo are changed as the robo is moved in the locations. Okay, some part of quaternion, some configuration of the robo will change when the robo moves in the configuration space. Okay, and as the robo moves in the configuration space, the C is observed as the configuration space here, the entire global space, and where the obstacle is also a part of a configuration space. So we take here like C abs, C OBS, or configuration space, which is occupied by the obstacle, is C OBS, which is also a part of or subset of the entire configuration space, right? And in this case, that means what, the obstacle lies within the configuration space, and this obstacle also has a quaternion. Okay, and this may be a big obstacle or a small obstacle, or the obstacle configuration may be similar to the configuration of the robo also. Okay, here I again repeat that what is configuration is. The configuration is the space occupied by the robo basically here with respect to the configuration space. Okay, and if you say the obstacle is also present in the configuration space, the configuration of the obstacle also will be represented as what is called the quaternion once again. Okay, and the quaternion of the obstacle and the quaternion of the robo should not be same. Should not be same. The union of the quaternion of the robo and the union of the quaternion of the obstacle in the configuration space should not be yes, or the let us take that set elements of A and set element of COVS. The the union of A and union of what is called union of A with respect to COVS should be a disjoint one, okay, or otherwise you can say intersection of A and intersection of COVS should be 5, okay, and this is what we can say when there is no obstacle met by the robo, okay, and if you say that the robo has met the obstacle, that means what the quaternion of the obstacle meets without
Harsha,
yes, 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 yes.
can you please brief on quaternion because we have never come
Yeah,
across this word.
quaternion is nothing but a quadruple. It's a quadruplet which is something like x comma y comma z comma some alpha. Okay, and this is simple thing like left, right, bottom, top parameters of an object.
It's a
Okay.
four-dimensional object or a three-dimensional object we are looking at here.
Yes, if it is say if it is a three-dimensional space as a configuration space, then we will have here four elements like left, right, width, height, and everything. Okay, and depth also. Okay, and if
I
it is
cannot able to visualize. Can you show me something? I mean, because your explanation is pretty good, but I cannot able to visualize.
yeah, I'm coming to that.
Sure. Yeah, please show me some screen which you can say how this is how it looks like.
Shall we go into the paintbrush and show that?
Sure, sir. Wherever
Let
it is
me let me
comfortable.
let me go into that. Let us assume that this is a configuration space. Okay. This is the entire world. This is the entire world. What we have seen here. What we are seeing here. The entire space. Okay. Entire space and what you say here. The entire thing. This much is the configuration space. What you can say. Let us say this is the configuration space. Let us fill this here. So this is the configuration space, right? And here we are assuming that this is what is called the 2D space. 2D space is this. And we consider here a robo. We consider here a robo. So this is the robo placed. Okay. Consider here this as the robo. Okay. And this configuration space, when we say this configuration space will have let there be number of points. Okay. This configuration space will have the graduations. It's a Cartesian plane where there are so many locations in the configuration space. Okay. Consider this as a obstacle. when you consider this as an obstacle, here you can see okay, this is a robo, and this is at a location called here, what do you say, a, you can say this is a location. Okay, location like this, this is B, this is C, this is D, let us see, this is 1. Okay, and here this is a, these particular two cells A1 and A2 are the two cells which are nothing but the location which is occupied by the robo. Okay, and if you go again like this, E, F, G, G3 and G4 are the G3 and G4 are the locations of the obstacle. Okay, here like what we have A1, A2 and G3, G4. This A1, A2 are the configurations, and G1, G3, G4 are the configurations. Similarly, you can also have what is called this coordinate, like an XY coordinate. We may consider it as an XY coordinate horizontally as X coordinates and vertically as Y coordinates, and where you can put here A comma 1 is the coordinate. A comma 1 is the coordinate. Okay, and this is simply for a two-dimensional space. That is for a
Are you talking? Because I'm not able to listen you.
yeah, I am talking, I'm here.
Sorry, because we lost your voice.
No, sir, I'm talking continuously.
Okay, probably because I lost your voice in between.
No, I'm talking continuously. You have to just
Okay,
listen.
I was up to with you. I was there up to A comma 1, the coordinate of A comma 1.
Yeah, I am continuing.
Ah, okay, you are continuing. Fine.
I'm continuing, right?
Yeah, sure, sir.
What about everybody? You are only listening, or others are also not, just not listening that.
There is a break. I
Yeah,
don't know.
we can hear you.
Yeah, I think everybody are listening. This voice is it audible to you, everybody now?
Yes, sir.
Yes. Right. So here a quaternion means that location. What we have, the left, okay, right, width and height of the object. Okay, and for a 2D case you can find like this, a 4-element quaternion, and for a 3D case you can say left, right, width, height and depth of the object also. Okay, so these are the basic things which we can say. 2D, in the 3D, in the 2D case, in the 3D case, you can see the quaternion is the configuration of, it defines the configuration or the locations of. See, it's a mathematical representation of the configuration space, and in the mathematical representation of the configuration space, we have objects, robots, and obstacles. Right? Here is this now. We are getting into see that means the properties of the quaternion are the elements of the set, and if the two elements of the sets, if the sets of if the elements of the two sets are same, that means what? The object has been superimposed by the robo, or robo has superimposed by the object. Okay. Right. Yeah, let us see here. So here we call this as A of Q. A of Q is the location. A of Q is the representation of the robo with the configuration called as Q, and O are the O. What is called O? O is the obstacle. Okay, and here with respect to the configuration space, as all these element, all the points of the robo and the obstacle are available in the same configuration space. Okay, as all the sets are available in the all the sets of the robo and all the sets of the obstacle are available in the same configuration space. So we say that these are all the closed sets. These are all called as closed sets. And if any of the points or any of the sets of points or quaternion configurations of the points are beyond the topological space or in the what's called configuration space, then we call them as open sets. Open sets means where they are the new sets or new points where we can venture to go for a new motion plan. Okay, and the points which are available possibly for defining a motion plan and defining a obstacle what is called encounters or whatever, then these are all called the closed sets or closed points. Okay, so almost all the leftover configurations of the C is that what is called, they are called as free regions or free spaces. Okay, and one more important thing, as we can say that these two cannot, the obstacle and the object cannot be superimposed. The obstacle and the object, both of them cannot be, the obstacle and the robo, what we say, robo cannot be superimposed, right? Robo cannot go and sit on the object, or obstacle cannot come and sit on the robo. Okay, and that is not a hypothetical thing, theoretical thing, right? As a fact, what we have to do is either the robo should reach to the points of the region of the obstacle, or the obstacle comes into the regions of the robo. Okay, see, they just only collide. They just only collide means what? The borders of the robo and the borders of the obstacle only touch together. That's all. Okay, and they do not really overlap the entire set of quaternion of both of themselves. Okay, what they do is simply some of the quaternion sets, some of the elements of these configurations of A and some of the elements of the configuration of the obstacle will get matched. Okay, when they get matched, that means that they are experiencing a collision. They are experiencing a collision, and thus by identifying the collision, we say that this obstacle is detected in the okay. Okay.
So Harsha, here C is
Here
the
INT is
configuration
used, the
space.
INT is used for interior. Okay, INT of O intersection INT of A of Q means the interiors of the robo and the interiors of the obstacle. If that is, if the intersection of these two interiors are phi, which means what? They are not intersecting, they are not colliding. Okay, if the interiors are intersecting, and if there is some kind of a common elements of the quaternion, then that means that they are colliding. Yes, yes. Please come up. Please come up.
I'm sorry. I'm sorry. Okay. So when we are saying the intersection of object as well as the quaternion are at the same pi. So how did we understand this pi? 3.1.4, 3.14 is the pi value that we are looking here. Or what do you mean by pi here?
Phi is an empty set. Phi.
Sorry.
It is a phi. not
Phi.
pi.
Okay.
It's not
Okay.
pi. This is not pi as 3.14 or 22 by 7, right? This
Yes,
phi,
exactly.
phi means it's a set theory. Phi means in set theory a null set, okay. So interiors of the object and interiors of the obstacle and interiors of the robo, if any of these, that is the configurations of these two, if they are intersecting, and if the result of the result set of this intersection of these two sets is a phi means what? Null set. No configurations are common among these two. Intersection means you know very well. Intersection
Yeah,
means
correct.
the common elements among the two sets is the intersection. If there are no common elements of the two sets, that means what? The two configurations are totally disjoint. When the two configurations are totally disjoint means they are really in the configuration space very far away. So there is no chance of collision here, right? So we
Yes, sir,
cannot say
exactly.
that this object has been collided with this robo, right? So we detect it as an obstacle only when there is a non-phi, non-null object here, right?
So you mean to say the pi has some value attached?
Yeah, another set, a set of values will come up, okay. As
Okay.
we say, the quaternion, as you have asked me the doubt regarding that, there are four elements I told you, and one of these elements will be null, and some of them will be some values also. Okay, because if left of the obstacle and if the left of the robo are matching, and if others are not matching, then what do we say? At least if one point is matching, then we can say that is they are hitting each other. Okay,
Yeah,
the
there is a
coordinates
high
are hitting each
possibility
other.
of collision happening.
Yes. Okay. So here I use what is called int means the interiors of the regions. The interiors of the regions of the obstacle with respect to the interiors of the robo. If these two are matching, then that means they are collided. Okay. Like this, the boundaries are intersected and they are observed as what is called, right. So this thing which I have given you some little information about what is called the fundamental requirements which we have to understand. We will get into the program things. Pygame simulators. So using Pygame, we will be doing some robo simulator which will demonstrate about obstacle detection, obstacle identification, path planning, and everything. Okay. So I would like to you people open your Python ideally and get ready with the Pygame, and we will we will start in another 5 minutes. We will have a break of 5 minutes. Okay, Shinu madam, shall we have now a 5 minutes break?
Yes,
Yeah.
so we can have a break for
Shinu,
5 minutes.
we will have a 5 minutes of break and we'll come back. And after the break, we will discuss about the programming aspects of this, and we will do some implementations on simulator. Okay. Thank you. Yeah, welcome back. Let us see the small simulation about a rectangular robot moving along and detecting the collision. In a given configuration space, we will say that there are no objects or obstacles as yet, and we will move that object as a rectangular robo, and this robo will reach the boundaries of the configuration space, and that will stop. We will prepare the simulation board for the robo simulator. Yeah, we will define a name to this file. Name of the file is initial collision. Let us initiate the position of the rectangular robo. The position of the rectangular robo in the 400 by 400 is almost all at the center of the xy of coordinates of the rectangular robo. Almost all we are defining here what is called the quaternion of the robo. Okay, width is this and height is this. This is the configuration of the robo. And as already we have seen in the last discussion, if you remember, we create a while loop to simulate activities of the robo simulator. We would like to move the robo according to the key presses, what we say, the left arrow, right arrow, up arrow, and down arrow. Are you following? Am I audible?
Yes, sir.
Please follow this. As if you can type as and when I am typing, you will achieve the result very quickly, and no need to waste time. We have many programs we can solve. Okay.
I'm getting an error. No available video devices.
Why did you run right now?
Oh,
Do you
okay.
have Pygame
Not
installed?
okay, fine. Got it. I didn't run. Oh, sorry. I'll
Why did you
stop
execute
running.
now? I did not execute the program right now, right?
Okay,
I'm just
yeah, sure.
typing it, right?
Yeah,
Kindly do
okay.
type. Okay, as let us first build the simulator first. We will also define here a variable called as velocity of the robo in 10 units. Of course, 10 milliseconds. And as per this, we will also check with the coordinates As you move leftwards, the x should be always more than 0. Until x is more than 0, then only you can move leftwards. Similarly for the y-axis also. Ensure that you have typed all this code in your systems. I think you have typed this program. Let us execute this now. See.
Can you please share the code, please, one time? We are almost done with the coding.
Surely, I will copy paste it in chat box.
Sure.
Just see here. Yes, it is moving. It is moving. Left, right, bottom, up. Okay. And if it goes to the left margin, see what happens. What happens? See, it's not going beyond the left. It is not going beyond the right. It is not going beyond the bottom and also the top. Okay. So here at the boundaries, it is experiencing the collision. The rectangular robo is moving in the configuration space, and at each and every border or the boundary, it is experiencing the collision. Okay, this is what is the fundamental thing. Please take this code and run it once and let me know that everybody have executed this program completely.
Still, I'm getting the error video system not initialized.
Yes, please come again.
Still, I'm getting the same error video system not initialized.
Video system.
Yeah. Can I share my screen?
Check it once possibly.
Yeah, I have typed along with you and I can share my screen. You can have it.
Please do it.
Yeah. So this is the code that which we are doing.
I did not.
So import pygame initialized BORD pygame display.
You are doing in Anaconda?
No, I'm doing in a collab.
No, this is not a notebook version of the code. You will get this kind of error because it cannot connect to the video system, right? You have to do it in Python IDLE only. Please try it in the Python IDLE, sir.
Oh, this is executable only in Python ideally.
Yes, yes, yes. Have you installed Pygame in this? Yeah,
Yes.
it is installed.
Yeah, it is installed. In the first line itself, I installed it.
So where is the error? Let me show the line.
Yeah, sure, please, sure.
Exactly.
See here, it is giving me the error.
Board is equal to display.set mode. This needs a VDU, visual display unit. So in Colab, it cannot connect to the VDU of any system. And that is the problem where you cannot do this. Yeah, this is what. Yes. Kindly do it in Python IDLE. You will get the result surely. Okay, please. Here also it should come. If you have done in Anaconda, it should come actually.
No, I understand.
Anaconda,
But
if you have installed in your local system, see, Colab cannot access your local system devices. Local system hardware, local system setup cannot be accessed by the Colab. Colab is only for testing and running the AI algorithms which are not related or not connected to any kind of peripheral devices.
okay.
Local peripheral devices cannot be accessed using Colab. Go to Anaconda possibly, or otherwise go to the IDLE is the best solution for that.
Sure, I'll install it today. Thank you.
Have you executed?
Yes, sir.
Which one? Which one? Sabyasachi?
Yeah.
You got that? Rakesh Kumar, have you executed? Okay, good. Rajanna, please let me know that you have executed the programs. This program. Vishwanath, yeah, you please execute the program, and if you find any difficulty in running this, you let me know in the chat box, or you can talk to me. Okay. So we will get into the next step. In this program, what we have done is a rectangular box colliding to the boundaries. Now we will take two boxes, and let us see how that does collisions, and even the two boxes may also collide. Let me see that first of all. Yes. We will do in this way. As we will be using the time, we have to import all other API for this time-based API. Now, let's go with this 400 by 400. Pull in the argument. Okay. Now let us start the clock. Here's the clock. We will do this as an automated movement of the rectangles. Automated movement of the rectangles, and these two rectangles in the board will be the two rectangles in the board will be moving along and colliding to the boundaries and colliding to each other also. Let us see this.
Can you come again? Why the pygame dot time dot clock function was invoked?
We will automatically move the robo according to the time ticks instead of we interacting with the time robos.
Okay,
Here
so
what we plan now here is the two robots will be moving along in the board, and we will see that their collision status.
okay.
The two robots are initiated with the rectangular configurations. For detecting collision, here we have collide object which can be returned by the rect object using the API collide rect, whether two rectangles are colliding or not. Here we can find whether robo A is colliding with robo B or not. Results a Boolean value. If true, then this robo A is drawn, robo B is also drawn on the board. Another configuration, color representation. Okay. Let me know that you have coded this and this program. This is a kind of a one-way collision, you can say. And there is a collision, and this has to be, yeah, it is an infinite loop, so there is no response. Look at this. This is a two-way collision. The both robots are colliding and recoiling back. Okay. And this goes out of the loop when you are trying to change the location of the board. The board update we have not done, so we have done only the board interior updates. So it is in the infinite loop and it is hanging. But what is done here is okay. So just copy pasting this code into the chat box. Try this once, execute this program, and let me know the yes. Rajana has not turned up today, I think so. Are you there, Rajana? Please copy this and execute this and let me know the result. That collision takes between two rectangular robots. I hope you have executed this program. If you have any difficulty, if you want me to explain, you can run. Yeah, Sabyasachi, it goes into an infinite loop because we have not tracked any key stroke here. You can put any key event here. Okay, after putting any key event, you can trace for any X key or any Q key from the keyboard. And based upon that, you can invoke the pygame.quit so that it will terminate the program. Otherwise, it will be a while run loop. While run loop is always a infinite loop here because run is equal to true, right? We can also try another version of this collision with mouse. Let us try with mouse. P1 is the robo one. You keep typing also as I am typing. And read the mouse position for the Robo1 slides with Robo2 after the mouse has been moved onto that, and if that is moved, then change the color of it's a collision, else the color is white. Collision, there is a red, otherwise so you understood the statement here. Collide is equal to 255, 0, 0 is the red RGB. This will be assigned to the collide variable only if the collide is true, otherwise white color. Letter board will be filled with black. Go. Quit the program. Okay. With this is a program with mouse, collide with mouse. So here we have a ease of moving into the internal configurations of the robots. Run this and see. Yes. Yeah. You can see the mouse. Mouse. As I move the mouse, there is a green rectangle. And if this moves onto the obstacle, see the color of the obstacle. The color of the obstacle changes to red because the coordinates of the mouse. Here our mouse is handling the positions of the robo. As the mouse moves, the configurations of the mouse or the configurations of this robo intersect with the configurations of the obstacle gets red. And when they are not intersecting or when they are not colliding, that is here. Yes? Yes, this is the program. Check it right now. I am copying it into the chat box. Right now, everybody. Mr. Vandanapu. Mr. Vandanapu.
Hey, my name is Gopinath. That's my surname.
Yeah, that's what I could not recognize. Sorry, I'm sorry.
That's okay. It's wrongly displayed there.
Did you?
Okay.
Sorry. Okay.
Yeah. Basically, I have to take my I am working on my personal laptop. I connected from the office laptop.
That you worked in Jupyter or Collab, right?
Yes. That's the reason I'm working on my personal laptop where I cannot key in the message.
Have you installed an idle?
Yes, it is working fine for me. All the code is working fine for me. Yeah.
Okay. Thank you. Mr. Suresh, please respond in the chat box if you have exported the program successfully. Vinia, James, Yashashwini, all others. Kindly respond in the chat box after you have executed the program. Okay. Only 4 people has executed. The remaining people. Rakesh Kumar. Rakesh Kumar, please tell me your status. Rakesh Kumar, please tell me your status. Guru Shant Murthy, please tell me the status that whether you have executed the program or you have any difficulty in installing the idle. We have taken here the examples of all rectangles and yes, yes, someone is talking. Please come up. Okay. We have seen so many, so for the examples of rectangles, and we know that rectangles are having the right configuration as left, right, and width and height. And let us see about a non-rectangle, a non-rectangular base, a robo with a non-rectangular base colliding, and how it reacts on this. Let us see the code for that. These lines are very common lines when we come into that. Okay, now what we are going to see is a non-rectangular base robo base with a non-rectangular robo with a non-rectangular base, and how it is in the collisions and obstacles in the configuration space.
Harsha, you're on mute.
Sir, yes, sir, yes, sir.
You're on mute.
Yes, sir, yes, sir, yes, sir. Yes. So here we have two non-rectangular shapes, and in this Pygame API we define the non-rectangular shapes as sprites. So we have a sprite A and we have a sprite B. These two are the two different sprite logos, and they move on the board, and as they move on the board, there will be collisions, and we will be tracking the collisions also. Here, all the sprites what are described will be defined as into a group. So there is a sprite group. Sprite group, okay. We'll run the sprite group. Only the definitions and configurations take time, but after that we execute, we will see the result of the two sprites, and sprite here is moved with the mouse action, and we check for the collision. Because they are sprites, the collisions are taken with an API called as sprite collide. This is sprite collide. And there is another group which we can create called as test group. This one we want to test as whether it is collided or not. The sprite B requires the sprite B requires to be tested whether it is collided with other groups or not, other sprites or not. So here in the sprite A, we give whether group is tested for collision. It is a bit longer sentence that we have to see maximum mode. Yeah, that collide. Sprites group are drawn on the board. Sprites are drawn at once on the board. Each object in the collision. So here we take for all the elements of the for all the sprites in the group, for all the sprites in the group which are colliding. They become white color. During collision, the width and center of the each collided sprite should match. Okay, this is the code. Let me run this and see. There is no comma here. Sprite spelling mistake. Okay, you can see. So now it is not rectangular, it is circular. Even on the circular shape, you can check. When this is colliding with this, the border of this obstacle becomes white. Calculating where to calculate this. Right. Okay. Yes. There is a slight aberration in this difference. Okay. Circular. You see the circular, it is not rectangular now. A robo with a circular base, if it moves on the configuration space, how the obstacle can be traced. If you come to this nearer, even here, you can see the resolution here. The corners of the rectangle generally comes out of the arc of the circles, right? So even if they are intersecting, it is not considering it is as a collision because it is in a circular shape. Okay, please try this once. I'm sharing the code. Yeah, it is a circular object now. Because here the configuration is different. The configuration here is the center point and the radius. Okay, and the center point and radius of the obstacle with respect to the center point on radius of the robo base are checked here for the collision. Sprite to sprite collision, and that's why here we have a special API called as sprite collide API is there, which we can test for sprite collision. Please try this and let me know the status of this in the chat box. Has anybody has copied this code? Please copy the code. Please copy the code and execute this once and tell me, let me know that.
When the two circles are coming together, collision, we
Yes,
are expecting to change the color of the boundary, correct?
Yes.
But what's happening is there is a lag in it. Like what I mean to
There
tell,
is a slight aberration that we can change.
how do we do that? I mean, we can increase the time, or how is it?
No, it's a slight aberration that you can see in the screen right now. Are you seeing this?
Yes.
Yeah. Here you have the sprite A. Okay.
Okay, this sprite is an API for the collision you are telling, right?
It's a definition of the circular based robots.
Okay.
This is another one, and here I have given 40 and here I have given 80. You can change it accordingly. And one more thing, I have given here intentionally 90 than this.
80 and 90.
Yeah, you can appropriately experiment on this.
Okay.
You will get it exactly. The functioning is coming. You can just change
Yeah,
this
the function is coming,
value,
but the after
value,
collision happen, it is showing the color change.
And this also you can change. Based
Okay,
upon
that is
these values, you can get
inflate factor that we have to change.
Yeah.
So that is the one that will change the color.
Yeah.
Okay.
And this you can identify what this collide is doing. What this collide is doing is, this is returning almost all the collection, a list of all the values which are colliding with the obstacle, and all the elements are taken here. Okay, in this example, what is actually happening? The mouse is the sprite A. Sprite A is moved with the mouse. Okay, and sprite B is static. Sprite B is static. You can compose some other sprites. You can compose some other sprites. You can enhance the region, and you can make the mouse move and move the sprite A to different other sprites also, and detect the collision. Okay, understood. And this will show the border for all those which the collision has been occurred. For all the obstacles in the board which the collision has occurred, this will change the border. This is to change the border. When the collision occurs, change the border is this. Okay, you may now put another thing like sprite C in the same board and give another configuration and give a location also here. So here is the location. See, in the sprite A, this indicates the color and the coordinate where this sprite is placed and the radius. Okay, and this another color, coordinate where the sprite is placed and the radius. Okay, so these are all given here, right? You can change it. Okay, you can change it and you can try.
So 40 is the radial distance between the two objects.
Yes, yes, yes.
So are we not considering the diameter, or I mean it's
that is the, see, because the base is circular, 40 is the radial distance between the center of the base to the surrounding circumference of the base for each sprite. It is not the difference between the two sprites A and B.
sorry, I lost with you.
Okay.
Can we show it in the diagram? I mean, like, take some.
Yeah, you can very well execute and see. Because the mouse is here by default, it appears. Okay. This is the position first of all, and when the mouse moves out of this is the position. Okay. You can check it here. Let me cancel that program which is in the execution. Yeah, it is cancelled. Now you can check it here. You can now see the default things. Okay, you can see the, can you see the default thing, default position of the sprites?
Yes.
This aberration you say.
Yeah, see, that is what I mean to say, because after collision, after some time, it is.
Yeah, here, top left corner.
Probably yes. Yeah. For me, it is bottom.
Mm, you are getting it in bottom side.
Yes,
Top.
I change it. Yeah, that's okay. Please go ahead.
Okay, give it as 40. This is slight aberration that we have to find it out. We'll see that. See, I'll get back to this.
Sure, Harsha, sure.
Okay. Right. Now, as we discussed in the last session, moving the object in the direction that in our last class we have discussed about that. This is done with orientation. I have done the code with orientation that you can see. Just a second. We will convert this into the automatic. It's now in the automatic mode. We'll convert this into the manual mode and see. That is first thing.
Sorry.
This is in the automatic mode. Actually, this was in the last session we were discussing.
Yes.
Shown in a earlier version which I shown that orientation was not shown. Orientation now I will show you that. You can see. This is set to automatic. When we have manual control, we have actions, and when we have automatic control, we have actions. Initialize this to manual and check. You can see here. You can see this is smoothly orienting towards directions. Means this has to be accelerated manually. And the image sprite or image which is shown here. smooth directions. Okay, this is manually done, and we can do it in the automatic mode. Here, if it is set to automatic, for automatic control, here we have the operations. For any set angle, it will be moving forward, or the motion as forward or backward. Okay, let's look at this. This is the target. It is moving towards the target. Here we click on this. In the automatic mode, it is moving towards the target as we select any random location. Click on any random location. Let us, I think you are able to see the mouse pointer. Click on any random location. It changes the orientation and moves forward. You can observe the way how it decides to check its orientations based upon the angle which is nearer to the object. Right? I think this code, I think I have already shared to you. This particular code has been already shared to you. Thing is in this line. In this particular line, almost that is the line number 40. The line number 40, we have to change the control, whether it is a manual or automatic. Okay, this is almost all. How many lines? It's 177 lines. So here the robo is the car, and it is moving in both manual and automatic directions. It is shared. The code is shared into your chat window.
Harsha, can you please share in the LMS?
Yeah, I will do that in later. Yeah.
Because sometimes, okay, yeah.
Yeah, understood. Last class also I've given in the WhatsApp that some parts of the programs. This also you can take. I will surely share it in the LMS.
Mm.
Yeah, right now I'll do it now. Yeah, it is available. You can check it.
Please share the link of the LMS. I can't able to
Yeah,
find
yeah,
it. Once it is uploaded.
yeah. It is shared, no?
I got the code in the messenger, but LMS I have.
Yeah. Anyway, it will be done. Anyway, it will be done, Mr. Nanapu. Okay. Right? So you please try that and check out. Yeah. You try both the manual mode and as well as the automatic modes. Try both the modes, manual mode and automatic mode. And in the automatic mode, the robo moves to the location wherever you request that by clicking on the mouse on the board, the simulation board. Okay. Let me know any interaction on this if you have any, if you want any clarifications so far what we have discussed for the other 15 minutes, and after that we'll go to the lunch. Yes. Vishwanath sir. Vishwanath. You try this program, try to move two robots with a circular base or a rectangular base in a board randomly and detect the collisions. If there is a collision occurred, then change the borders or the colors of the robots of each. So you can do this as an assignment, a very simple thing. So far the codes whatever we have given, the programs whatever we have given, all these codes are very important and they are referential for writing this assignment. Where you can consider two robots, where these two robots or two moving objects are available on a board, simulation board, and these two robots are moving randomly. And when the two robots are moving randomly, these two robots may collide or may not collide. And when they collide, change the colors of these two robots. When the collision occurs, change the color of the robots into some red color or border of that into a white color, so on. Okay, and if they do not collide, just they will be moving around. And also you can write a text message, as you can see in the code just now what I have sent. The text message is written as automatic or manual. You can see the syntax of the lines as how to write as automatic, how to write as manual on the board. Okay, so which indicates the mode of the board, whether in the automatic mode or in the manual mode. Okay, and see in this example, while moving the two robots randomly, when they clash, when they collide, highlight the colors. When they do not collide, do not highlight the colors. Let them move in the board randomly. And if they collide with the walls, indicate the wall direction and also the highlight the wall, which wall it is hit. Okay, so you can write with the draw rect command, and you can write a message in the bottom right corner that all the statuses of the movements of the robots in the total board, right? So try it once if you can do. Let me know. Let me know any difficulties or any doubts if you have on this when you are implementing this. Two robots moving randomly in a board, simulator board, and hitting each other, and as well as hitting the boundaries. Yeah, right now it is uploaded in the LMS also. Kindly check it in the LMS. Mr. Suresh, please check it in the LMS. You can find out.
Sure.
Yeah, loudly please. Loudly please.
Yeah, I'll check it out. Thanks for it.
You please check that program in the LMS. Just try executing the program both in the manual mode and the automatic mode. Right? that is executing, and we will have some other programs in the afternoon session about motion planning and also the A star algorithm, RRT and A star algorithm, right? Please come up with any clarifications, doubts regarding sessions what we have done so far. Okay. Did you copy it from the LMS? Did you copy it from the LMS, sir? Suresh, sir. Suresh, Mr. Suresh. Did you copy it from the LMS?
I'm doing it.
Okay, okay.
We can have a lunch break now. We'll join back at 2 o'clock.
After lunch, we will discuss about the A-star, motion planning, and RRT.
Okay, sir. Thank you.